which simulates the transfer, diffusion, and chemical reactions of pollutants. On the other hand, the statistical model focuses on using methods such as machine learning to summarize the statistical characteristics of historical observation records. With the rapid development of the machine learning methods these years, training for good models is becoming more and more data hungry. The increasing demand for data makes the former data collection methods inadequate. Originally, urban air quality datasets are usually collected by a few stationary, high-precision professional measuring stations. They are accurate, well-maintained, but also expensive and need professional personnel. Only very few organizations with sufficient technical and financial reserves are able to establish such measuring stations. However, in urban areas, factors related to air quality may change rather rapidly, so we need more sensors to achieve higher spatial and temporal resolutions for a clearer view. A larger sensor network with different sorts of mid and low-cost sensors is everything but a new idea. The SmartEQNet project is one among them. The project is an urban air quality measurement network that observes metrology and aerosol measurement data in fine granularity. The original intention of the project was to integrate a wide range of measuring equipment of various available price and quality classes. The project was started in the year 2017, and the model region of the project is selected as Augsburg, Germany. The measuring equipment involved in the SmartEQNet project could be categorized into 4 parts. The first part is so-called high-accuracy scientific measurement technology. In the SmartEQNet project, there are 4 state air quality monitoring stations which collect PM10 readings. A ground-based remote sensing network consisting of 3 celliometers and a radioacoustic sounding system, which observes cloud and wind by height profiles. The third existing network is a local meteorological station network consisting of 7 stations, collecting various meteorology properties such as temperature, wind, pressure, precipitation, and so on. The characteristic of this part of sensors is that they could provide observations with very high accuracy, and the temporal resolution is also satisfactory. However, due to the sparse number of stations, the spatial resolution is relatively poor. The second part of the project is consumer-grade and low-cost measurement sensors. During the project, we deployed 6 GRIM EDM164 OPC sensors, which have relative higher precision and used as reference devices, 22 GRIM EDM80 NEPH sensors, and 35 GRIM EDM80 OPC sensors, as well as 84 cloud sensing nodes, which are composed of a NOVA SDS011 ultrafine particulate sensor and a Bosch BME280 sensor. All the above-mentioned sensors can provide PM and basic meteorological observations, and they together constitute the main body of this part. Of course, we also have some other data sources, such as data from the devices deployed by the Helmholtz Center Munich. In order to save time, we will not list all of them here. The characteristic of this part of sensor is that, compared with the high-accurate scientific measurement technology, they trade off some precision for higher spatial and temporal resolutions. The third part of the project is location and period-fixed mobile measurements. Such measurements were carried out between December 2019 and September 2020 by 2 UAV systems. Both UAVs are equipped with low-weight weather parameter sensors and particle counter, and were flown at a fixed location and a fixed period. Such measurements observe the detailed 3-dimensional dynamics of the lower atmosphere at a certain location with fine granularity. However, since the UAV flight requires the operation of the pilot on the ground, it can only be carried out regularly at a certain frequency, thus cannot fully cover the time dimension. The last part of the project is so-called intensive sensing campaigns. During the campaign, mobile measuring devices were installed on backpacks, bicycles, and trolleys, and were carried through the city by the participating personnel. For this part of the project, the coverage in the time dimension is more limited due to the effort required to organize activities. However, this part of the data has extremely high coverage in the space dimension. The above is an introduction to the basic situation of the SmartEQNet project. In the following part, I will compare the SmartEQNet 2020 dataset with some other candidates to show its competitive. 3 candidates are selected for the comparison. The first one is Beijing Multi-Site Air Quality Data dataset. This one was selected as a representative of traditional air quality dataset, which was collected by high accuracy stations. This dataset including data from 12 official air quality monitoring stations in Beijing, China. The second one is Open Sense Sewage dataset, comes from the Open Sense Sewage project powered by ETH Sewage. In this project, sensors were mounted on top of trams and were carried through the city area of Zurich. The third one is Luftdaten.info dataset, Stuttgart area. Luftdaten is a citizen science project which mounted an enormous number of low-cost sensors worldwide, especially in the Stuttgart area, Germany. As for we are discussing urban air quality monitoring here, so we only choose the Stuttgart part of the dataset here for comparison. In the table, you could see the time span of each dataset, and if the project related to this dataset is still running. You could also see the area of the observed area. We use the axis-aligned minimum bounding box here to calculate the area. You can also see the total number of data streams, and how many from them are stationary or portable. I define a data stream as a group of observations from a specific device and observing a specific property. For example, if I have a box which could collect PM10 and temperature data in my office, then we have 2 data streams here. If my colleague has a same one in another office, then we have 4 data streams in total. As you can see, the Beijing dataset only have a very restricted number of high-accurate stationary data streams. The OpenSense dataset only has portable data streams and also doesn't include any reference devices. As a citizen science project, Luftdaten dataset achieved an enormous amount of sensor deployment. However, the dataset also suffers some drawbacks because of it. All sensors in Luftdaten.info are low-cost sensors, no reference devices included, and most of these sensors are deployed by citizens, which may make it difficult to assess whether the deployment is qualified. And these factors reduce the overall quality of the data, making it more challenging to extract reliable information from the dataset. On the other hand, our dataset, as mentioned earlier, is a combination of stationary devices and 3-dimensional observations with different level of precision. The second last row is maximum data streams in one day. This metric is important because for those networks that contain low-cost sensors, it's quite usual that we establish the whole network step by step, which means new data streams come into the network continuously. However, at the same time, some of the old data streams are temporarily or forever lost their function. Therefore, this metric can reflect the actual scale of the network more objectively than the total number of data streams. The last row, spatial density, was calculated by dividing the area of observation by maximum data streams in one day, which means when the network has achieved its largest scale, how many square kilometers on average there is one data stream. It should be pointed out that the sensor distribution of urban air quality datasets is never uniform. It is usually dense in the city center and sparse the closer it is to the suburbs. But for different datasets, the degree of density is different. The OpenSense dataset and Luftdaten dataset only passively shows this feature as a result of the data collect method chosen for the project. For the OpenSense dataset, the reason why the observations are concentrated in the city center is that the tram traffic in the city center is relatively dense. While for the Luftdaten dataset, the main reason is because the population density of citizens in the city center is higher. For the Beijing dataset, although the location of the 12 monitoring stations was consciously focused on the city center, as a super metropolis, the area of Beijing's city center also exceeds 1,300 square kilometers, which is almost 10 times the total area of Augsburg. When the Smart QNet project was established, the distribution of sensors in the monitoring area was carefully considered. We chose an area of about 5 square kilometers as a core observation area, and a large number of sensors were deployed in this area. If you need a relatively small area to build a fine-grained model, then such a design will be ideal for you. In the second table, you could see which properties do this dataset observe. All of these datasets observe 2 kinds of properties: pollutants-related properties and metrology-related properties. As our dataset concentrates on observation of aerosol, we separate aerosol-related properties with other pollutants if other datasets observe multiple pollutants. In the last row, you could see observation density, which was calculated by dividing the total amount of aerosol-related and metrology-related observations by area of observation and time span, which means how many observations there are on average per square kilometer per day. As the last part of the presentation, I would like to talk about what chances you could see in the SmartQNet dataset. In other words, what can this dataset provide? Let me give some examples here. The first thing is of course about the modeling of urban air quality. In our dataset, we have a large number of observations, observing the model area with fine granularity. It can meet the requirement of statistical modeling very well. On the other hand, since we have also recorded a variety of meteorological data, so it could also be used for physical modeling. Secondly, this dataset could also serve to evaluate your interpolation algorithm. The data provided by the high-precision measuring station and the intensive sensing campaigns provide multiple possibilities for evaluation. Thirdly, the dataset provides a good chance for understanding the performance of low-cost sensors. Our project is a long-term, high-volume, low-cost sensor usage instance. From the dataset, you may dig out problems one will face when deploying such a low-cost sensor network. This will provide instructions for the next stage of not only our projects, but also any other similar projects in the future. You may also propose calibration methods for low-cost sensors which are working in a network. Our high-precision parts of the measurements could be used as reference. The first thing I would suggest is that the dataset could be used for understanding how coronavirus affect urban air quality. Our dataset provides a comparison between the corona period, which means the second half of the year 2020, and non-corona period. During the corona period, with the carryout of different restrict policies, reduced human activities may also affect the distribution of the ultrafine particles. By analyzing the difference between these two periods, we could get a deeper understanding of such effect. And maybe particulate matter could also be used as an indirect indicator for the reaction of the citizens to such restrict policies. A REST API that follows OGC SensorSync's international standard is already available for everyone who wants to access the dataset. Another available access to the dataset is a series of the dumped JSON files, separated by date. A CSV version of the dataset has also been prepared and will be uploaded later. So that's all for my presentation. Thank you for your attention.
Oh, thanks a lot. I have just let me check the chat if there is any questions. I've just a curiosity about this data set. Is it available a website from which this data set can be downloaded or consulted and can, for example, build some statistics or not?
Yes, it's currently available in multiple forms. As we mentioned in the presentation, the first thing you can use a REST-styled API to access the dataset, do all the search that you want to do, and we also gave out already a JSON version of the dataset, and the CSV version is already made and will be uploaded later. And about the download protocol, we have a protocol now for the SmartQNet project, but in this protocol, I have to say that the download link is still needs us to
under request maybe.
Yeah.
Yes, that's fine. So good work.
Thanks.
Thanks a lot. So I think that we can go on with the next presentation. Let's see the next presentation. The second speaker is Salvador Pedro, who presents the contribution and characterization of dynamic and thermodynamic features of African dust outbreaks over the Iberian Peninsula and Balearic Islands, trend analysis for the period 1948 to 2020. So please go with the video and then we will discuss on it. Thank you.
Good afternoon. My name is Pedro Salvador, and the title of my talk is Characterization of Dynamic and Thermodynamic Features of African Dust Outbreaks over the Iberian Peninsula and the Balearic Island, trend analysis for the 1948-2020 period. The main objectives of this work were the identification of the main synoptic properties associated to the development of African dust outbreaks over regions of the Iberian Peninsula and the Balearic Island, and evaluating their time evolution in the last 70 years. It's well known that the occurrence of African dust events has been identified regularly over regions of southern Europe since the last 20 years due to the availability of a number of specific tools. This way, it's been possible to demonstrate that African dust outbreaks trigger significant increases in regional background levels of PM10 in these regions and in adverse health effects for their population. However, before the year 2000, all these tools were scarce or even unavailable. For this reason, we thought that a long-term evaluation of the development of this type of event would be necessary to prevent future impacts. This has been the main motivation of this work. Two main tools were used in this study. The first one was the NCPNCAR Global Reanalysis Dataset fields of temperature and geopotential height at different atmospheric levels and time periods in the period 1948-2020. 8 regions of study were defined in the Iberian Peninsula Balearic Island domain, and the data corresponding to the grid points of the fields located over each one were extracted and analyzed. The second one was the record of African dust outbreaks identified with the Spanish reference method in each region of study in the period 2001-2020. This well-known and tested methodology has been described elsewhere in a number of reports, and the identification of the events is based on the use of meteorological tools such as air mass back trajectories computed with the high-split model, aerosol maps from numerical models, satellite imagery, or synoptic meteorological maps. This method also allows estimating for each episodic date the net African dust contribution to the PM10 regional background levels in each region. These contributions were obtained as a result of a statistical analysis applied to the 10 series of PM10 regional background daily levels registered in any region, which is also described in the methodology reports. Then they were used to classify an event as low, medium, high, and very high depending on the level of dust contributions. For instance, these are the episodes of different intensity identified in the southeastern region of the Iberian Peninsula in the year 2019. The methodology has consisted in calculating the daily mean values of 3 thermodynamic parameters over each region. The geopotential thickness in the 1500 hectopascal layer, the mean potential temperature in the 925-700 hectopascal layer, and the anomalies of temperature at the 850 hectopascal level. High levels of these parameters have been usually related with the presence of warm, stable, and dry masses, that is, with a potential origin in desert areas of North Africa. That's the reason why they were selected for assessing the occurrence of African dust outbreaks in our study. Next, we identified African synoptic circulation patterns by means of a circulation classification procedure using daily fields of 850 hectopascal geopotential height at midday. And finally, we analyzed the time evolution from 1948 to 2020 of all the days under African circulation types and their associated mean values of the 3 thermodynamic parameters to detect upward or downward trends with the tail-send method. This way, we obtain fairly significantly higher mean values of the 3 thermodynamic parameters in all regions during African episodic days than during other days in the period 2001-2020. The same result was obtained during any season of this period. These are 2 episodic days corresponding to intense African dust events with high levels of aerosol optical depth and surface dust concentration. They were driven by the high pressures located over the north of Algeria and Tunisia in combination with a low pressure center located to the southwestern of the Iberian Peninsula. The maps of the three thermodynamic parameters clearly described the low pressure center and the arrival of the African air masses from the southeastern sector of the Iberian Peninsula. Next, we also obtained in all regions higher mean values of geopotential thickness, potential temperature, and anomalies of temperature during African dust outbreaks of increasing intensity. This figure shows the results for the anomalies of temperature. These results suggest that higher levels of geopotential thickness, potential temperature, and anomalies of temperature result in more intense events, that is, with higher contributions of African dust. Then, we observe the existence of a clear negative latitude gradient for the mean levels of potential temperature and geopotential signal variables during the development of African dust outbreaks of increasing intensity. The opposite behavior, a positive latitudinal gradient, was obtained for the anomalies of temperature mean values. So, depending on the region, the intensity of the African event was associated to a specific range of levels of each of the three thermodynamic parameters. When it comes to the classification of the atmospheric circulation scenarios, we obtained 11 different circulation types, and in the period 2001-2020 most African dust outbreaks were produced under 6 of them. Most African dust events in all regions happened under circulation types number 1 and 10. They happened mainly in the summer period. However, other African circulation types, such as the number 2, were typically produced in winter. The other African circulation types were more evenly distributed along the seasons. What is important to know is the fact that higher mean levels of the three thermodynamic parameters were registered under the 6 African circulation types than under the other 5 circulation patterns. The highest mean levels were obtained for circulation types number 1, 10, and 6. The other synoptic patterns associated to the occurrence of African dust outbreaks were associated to lower mean levels of the three thermodynamic parameters, but they were still higher than under other synoptic meteorological situations that didn't transport African air masses toward the Iberian Peninsula and the Balearic Islands. Finally, we obtained statistically significant upward trends for the annual number of days under African circulation types and the associated mean levels of the three thermodynamic parameters over the Iberian Peninsula and the Balearic Island domain in the period 1948 to 2020. The same result, but with different values of the trend estimators, were obtained in spring, in summer, and also in winter. And also for specific African circulation types and periods of the year, such as the circulation type number 1 and number 10 in summer, or the circulation type number 2 in winter, or the number 4 in spring. In conclusion, we have demonstrated that African dust outbreaks over the Iberian Peninsula and the Balearic Islands domain are associated with the development of specific synoptic atmospheric circulation patterns and with high levels of some thermodynamic parameters which have been identified. Moreover, as the values of these thermodynamic variables increase in each study area, the dust contribution to the P and 10 regional background levels also increased. We also report an upward trend in the nominal number of days under African circulation types and the associated mean levels of thermodynamic parameters over this region in the last 7 decades. These results are in line with the exacerbation of warm conditions registered in Southern Europe and Northern Africa during the last decades, suggesting that climate change is also related with an increase in the frequency and intensity of African dust outbreaks in these regions. Thank you for your attention.
So thank you a lot, Pedro. So let me check in the chat if there is any question. No question. I've just to ask you if you have thought to some development of your study, maybe using some other techniques, spatio-temporal, for example, in studying this kind of phenomenon.
Well, we are still checking the usefulness of identifying African dust outbreaks by using thermodynamic parameters. So we are still not
thinking to other development.
Yes. Maybe we can still obtain more accurate parameters to define the arrival of the African air masses.
Yes,
so
maybe.
The study is still in progress, but we think it's a good idea.
Maybe to add some other parameters, yes. Or just compare different techniques.
Exactly, and combine with.
Or combine, exactly.
Yes, with dynamical models or.
Yes.
The main idea is to use information for many years in order to go back to identify these events and trying to evaluate the trends regarding their occurrence.
Yes.
So this is a first step, but we think that results are good.
Yeah. Yes, I think
maybe they can.
Yes,
maybe they can be refined.
Yes. Anyway, I think it is a very good work. Okay, thank you. Thank you for participating to this session. So let's go on a little bit. The next speaker is Sabrina Maggio, and the title of her presentation is Air Quality and Pollution in Apulia region, an analysis by multi-level approach. So please with the video. Thank you.
I can try.
Yes.
Okay.
We are on time, so we can just wait a little bit.
Yes, I think there is a problem with the presentation.
We just have 9 minutes in advance.
Okay.
Hi everybody, I'm glad to find you here at the conference. I'm Sabrina Maggio and I'm going to present the results of a joint study with my colleague full professor Sandra De Iaco obtained from a multivariate multi-level analysis regarding the air quality and pollution in Apulia region. Here the outline of my presentation. I will introduce the motivation of the work and some theoretical concepts on multi-level models. Then I will describe the data used for the analysis and I will present the fitted multivariate multi-level model. In conclusion, I will provide some final remarks. Air pollution represents a critical problem for urban areas and for their sustainable development, since it causes damage to human health and environment. Pollutants are characterized by concentrations evolving across time and space, and they can be transported in the atmosphere even over very long distances. The aim of this work is to implement a multi-level multivariate model to explore the prominent spatio-temporal factors which can influence air quality in Apulia region. The multi-level approach is a statistical methodology for the analysis of a hierarchical data structure with complex pattern of variability. This structure classifies the cases into non-groups with their own set of explanatory variables at each group level. The units of the first level are usually represented by individuals. Then, at the higher level, they are nested within aggregate units. The effect of groups on the response variable are evaluated and the variability at different levels of a hierarchy is also computed. The advantage of using multivariate multi-level analysis is the possibility to estimate I don't understand. I'm not here. There is no sound. Yes.
Yes, maybe the video can be transmitted again.
Yes.
So start
In
with-
other way, I can with my screenshot screen. I don't know.
I can ask the organizer.
Yes. I can transmit it with my screen.
So let's ask the. So, okay. The organizer is not answering. So maybe if the organizer does not answer, we can share our screen and then
Yes.
maybe better to share your screen and then
Yes.
we can see your video.
Yes. I can share my screen.
What is happening, please?
The video is stopped.
Please switch off your microphones,
Okay.
and we will start the presentation.
Okay.
Sabrina, have you there your presentation ready?
Yes.
Yeah, please display on.
Ma chi sta gestendo adesso questo?
We cannot hear. The volume is too low.
Just a moment, please.
Yes.
Oh.
Can I go?
No, io non posso fare nulla qui, non sono io, questo non è il mio schermo.
È lei che sta gestendo.
I have to share the screen.
Yeah, Sabrina, this is your screen.
Yes.
We have not control.
Okay.
Please go on.
Okay.
No. Vabbè, vediamo se riesco a farlo io da qui, dai. Proviamo, ma non ne sono sicura. Sì. Vediamo così.
I have to stop my presentation.
Sì, sì.
Have I to stop? Yeah, okay.
Ancora. Quindi esco. Senza voce. Stacco. Stacco.
I can share my screen in case.
No.
I don't understand why it doesn't work.
I don't know. I can try.
Can I share my screen?
Yes, just a moment.
Hi everybody, I'm glad to find hence high levels of this pollutant are registered. Figure B shows, for average daily ozone, a seasonal cycle with peaks in late spring to summer and minimums in late autumn to winter, which is largely driven by the photochemical production of ozone and the temperature. Figure C shows negligible seasonal variation of nitrogen dioxide average daily concentrations. The multi-level analysis has been performed by fixing 3 hierarchical levels. The choice of 3 hierarchical levels is justified by taking into account that the monitoring stations are considered as the highest level. The third level, represented by 23 monitoring stations of Apulia region, where the pollutants and meteorological variables are measured. And the days are considered as the second level, represented by 365 days of the year 2019. This is the period during which the pollutants and meteorological variables are measured in each monitoring station, classified by traffic station, industrial station, and background station. A multivariate structure is used to analyze the relationship between a set of independent variables and a cluster of 3 outcome variables, PM10, nitrogen dioxide, and ozone daily concentration. After analyzing all the dependent variables separately, the multivariate analysis has been preferred in order to test the joint effect of the explanatory variables on the 3 dependent variables. Computational aspects associated to the fitting process have been faced by using MLWin software. Now, this is to introduce the implemented 3-level model, where the multi-level analysis is computed. Here, a 3-level multivariate model has been implemented, and in particular, in order to assume a multivariate normal distribution of variables, the log transformation of the 3 outcome variables is used. And then a set of covariates has been selected for modeling purposes. In particular, the set of covariates has been selected for modeling purposes. The meteorological variables, that is the daily average measurements of atmospheric temperature, relative humidity, atmospheric pressure, wind speed and wind direction, rainfall and solar radiation. And finally, the type of monitoring station. The significance of covariates is tested by a chi-square test based on the deviance of the model. Then, the backward deletion procedure has been used in order to select the right pattern of covariates. The covariates which are not statistically significant have been neglected. At the end of this process, the covariates not statistically significant are the following: wind direction, solar radiation, relative humidity. Let's introduce the equation of the model. Note that the coefficient of the constant are assumed to vary across the second level or across both levels. And the slope of the covariates rainfall and temperature for PM10 are assumed to vary across the third level. From the results reported in the table 1, it is evident that there is a significant relationship, negative or positive, between the covariates selected and the cluster of outcome variables. The significance of the regression coefficients has been obtained from the whole statistics. The covariates selected are all statistically significant. From the estimates of the fixed part of the model, it is evident a separate effect of the covariates atmospheric pressure, rainfall and atmospheric temperature. In particular, atmospheric pressure has a positive relationship with all the 3 pollutants. Atmospheric temperature has a positive relationship with the particulate matter and ozone. and rainfall has a negative relationship with all the free pollutants. On the other hand, by analyzing the common effect, it is highlighted that the cluster of the free pollutants is negatively affected by the coverage wind velocity, traffic station, and industrial station. By focusing on the random part of the model, the estimated covariance matrices at the first level representing the space and the second level representing the time are calculated. And now some concluding remarks. The empirical results show a relationship between air quality and the type of area and the specific meteorological variable, atmospheric pressure and temperature, and wind velocity. In addition, the variability depends more on the differences of the first level rather than at the second level. In the future, the multi-level multivariate model will be improved by predictions and the geostatistical analysis of the residuals, since spatiotemporal geostatistical techniques provide useful tools to analyze and control the complex evolution of various variables observed by environmental monitoring networks. And a combination of geostatistical techniques and multivariate multi-level analysis would represent an advance in research and a novelty in the literature. And finally, the results could be useful to support national policies for environmental and health protection. I have also included some references for further details on the methodology. Thank you very much for your attention.
Thanks a lot for your presentation. Let me check the chat. I don't see any question. Okay. So, is there a question? No? I can see. Okay, so I think that we can go on. Okay. So now it's the turn of Gizem, Tuna, Tuygun, who presents the contribution estimation of ground level PM 2.5 concentrations with MERA2 aerosol diagnostics over the northwestern region of Turkey. Okay.
Hello everyone, my name is Gizem Tuna. I am from Gizem University, Department of Environmental Engineering. Today I will talk about the estimation of ground level PM 2.5 concentrations with MERA2 aerosol diagnostic over the northwestern region of Turkey. Actually, as we know that PM 2.5 pollution is a great environmental issue over the world. Recently, we know that satellite-based aerosol products they can provide a favorable characteristic, including broad coverage, high spatial resolutions, and long-term records, and they can provide a valuable aerosol optical that AOD is widely used dimensions parameter. It mainly represents the degree of the aerosol in the atmospheric column. However, as we know in the literature, satellite-based PM 2.5 estimations with AOD has still great problem producing sensitive, continuous, consistent and reliable PM 2.5 estimations over different regions over the world, since spatial and temporal gaps in satellite data cause bias in PM 2.5 estimations. So we tried to create a different kind of model to estimate PM2.5 concentrations using PM2.5 components. And we think that it could be more important than AOD data in the estimation model. Also, creating more reliable MERA2 PM2.5 dataset than MERA-derived PM2.5 concentrations over the region. Studies estimating PM2.5 concentrations with just using the reanalysis data are limited in the literature. The main objective of this study estimate daily PM2.5 concentrations over northwestern part of Turkey during the past 5 years using some machine learning approach. Firstly, we obtained hourly measurements of PM2.5 concentrations during 2015 and 2019 were collected, and daily mean concentrations were calculated. An XGBoost model was developed to estimate surface 2.5 concentrations, and then we did some comparison between observed, estimated, and MERA-derived PM2.5 concentration of the region. When we look at study area, you are seeing here the Marmara region. It's located in the northern part of Turkey, and it's bordered by Greece and Aegean Sea to the west, and Bulgaria and the Black Sea to the north. At the center of the region, the Marmara Sea is located. Actually, it gives the region its name. The largest city in the region is Istanbul. I think that everybody knows Istanbul as the really mega city located in the European region. The region is the most densely populated region in our country of Turkey. When we look at the ground level PM2.5 data, as we see in this figure, stations are distributed unevenly, and most of them are clustered in the urban area and mainly located in Istanbul. Ground level 2.5 observations were collected from the official website of European Environment Agency, and they are doing some validation procedures on PM2.5 data. We use daily average PM2.5 data from 48 active viewpoints from station to train and validate our machine learning algorithm. We use key reanalysis aerosol fields, including total angstrom exponent parameter, representing the size information of aerosols, and surface mass concentrations of dust, sea salt, sulfate, black carbon, and organic carbon. We also obtained hourly meteorological variables, including for example, planetary boundary layer, solar radiation, pressure, humidity, wind components, and etc. You are seeing here all the list of the variables of here. We included some spatial and temporal information into our XGBoost model, spatial variables of latitude and longitude of the grids, MERA grid cells, and temporal variables of year, month, and day were included our final model. We should process and integrate MERA to the concentrations before the modeling study. So we match all variables in space and time, accounting for the differences. Location of PM2.5 monitoring stations were used to match MERA 2 pixel for data integration. If we have more than one station located in the same MERA grid, we average all available PM2.5 measurement because they can provide all similar covariate values. Finally, we created some specific regression matrix integrating all variables from meteorologic statistical data, aerosol fields, and the additional temporal and spatial information. We finally obtain 17,200 samples to train and validate our XGBoost model. During the training and the validation approach, we divided randomly 80% for training and 20% for validation, and we repeated this by 10 times, and we know this means that this is a cross validation. 23 variables were used our XGBoost model, and we also calculated the importance scores of each variables our result. When we look at the results and variable important results in XGBoost model, 10 important variables in XGBoost model, including acceleration, angstrom exponent, wind direction and wind speeds, PBL, and the year as a temporal information, and black carbon and dust mass concentration from aerosol information. When we look at the model validation result, we achieve overall daily cross validation R 1.86. Actually, this is a really provide a strong positive linear relationship between the observed and estimated values over the region. We can say that our XGBoost model can handle some random variations in PM2.5 concentrations over a region and provide an acceptable modeling results and estimation results over the region. When we compare our estimated and observed values with the MERA 2-derived PM2.5 concentrations using the following equations, we see that MERA 2-derived PM2.5 concentrations mainly underestimate concentrations over the region. Actually, our estimation results and greatly higher correlations and represent the time series over the region. We think that it's the important point that MERA 2 data does not include any nitrate information in PM2 point components. So for our region, this causes significant underestimation because this region mainly has so much industrialized areas and significant nitrate concentrations over the region. We think that this is the main reason of this kind of great underestimation. And some points, MERA 2-derived PM2.5 concentrations has great overestimated values over the region. When we look at seasonal validation results, in general, every season, each season, model performance is slightly different. However, winter and autumn season lower accuracy because our model mainly underestimated higher concentrations over the region. These seasons are polluted seasons in our region. Spring and summer show similar accuracy and achieve higher accuracy than the polluted season, we can say that. In conclusion, the performance of MERA 2-derived PM2.5 concentrations greatly vary over the worldwide and depends on many factors like missing emission, roles of physical and chemical processes within a model because of its coarse resolution. Actually, this is the first study that used individual components of aerosol mass concentrations with meteorological data to estimate ground level PM2.5 concentration using machine learning approach over Turkey. We briefly say that our results show that MERA 2 aerosol diagnostics provide an effective tool for estimation of PM2.5 concentration using the machine learning approach, it could be used as an alternative method to mirror to the right PM2.5 concentrations. And the developed XGBoost model can be applied to long-term can be applied to analyze the long-term MERA2 datasets, and spatial temporal variation of PM2.5 concentration can be evaluated accurately over the region. Thank you for listening.
Thank you. I've checked the chat. There is no question. So we can go on with the next presentation of the same author, Gizem Tuna Tuygun, is presenting this contribution titled Estimating Intradaily PM10 concentrations over the northwestern region of Turkey based on MODIS using random forest approach.
Hello everyone, welcome to my presentation. My name is Gizem Tuna Tuygun from the Güzel University, Department of Environmental Engineering. I will talk about estimating intradaily PM10 concentrations over northwestern region of Turkey based on MODIS AOD using random forest approach. Actually, satellite aerosol products with favorable characteristics including both spatial coverage, high resolution, and long-term records provide reliable aerosol information over the world. Aerosol optical depth, we call it AOD, is widely used dimensionless parameter representing the degree of aerosol amount in the atmospheric column. AOD from various satellites and sensors have been widely used to estimate both ground level PM10 or PM2.5 concentrations. Actually, it's mainly used for PM2.5 concentrations over large areas, as demonstrated in the literature. So much study exists in the literature about this topic. However, satellite-based PM10 estimations with AOD has still some problems producing sensitive, consistent, and reliable data because spatial and temporal variability in relationship between AOD and surface PM concentrations, mainly location-specific, and data quality is really changeable. As we told before, AOD is a column integrated top of the atmosphere and column data and a function of shape, size, aerosol type, and number of concentrations. However, PM measurements representing the surface level aerosol particles over a region. So we just need some parametric meteorological land use variables to train and convert AOD to surface PM concentration. When we look at our study area, we studied over this Marmara region, and the region is located as seen here northern western part of Turkey, and it's bordered by Greece and the Aegean Sea to the west, Bulgaria and Black Sea from the north. At the center of the region is the Sea of Marmara, which gives the region its name, and the largest city is Istanbul in here, located in, I think that everybody knows Istanbul in European area. The region is the most densely and populated region of our country, and the main industrial sites are also located in this part of Turkey. We obtain hourly ground-based PM10 concentrations, and we calculate the PM10 concentrations according to satellite overpass time over Turkey. We obtain hourly measurements from our Ministry of Environment and urbanization website, and we conducted some validation study for data cleaning using some EPA documents. Finally, we worked with the 72 ground monitoring station in this study. Satellite AOD obtained from moderate resolution imaging spectrodiameter MODIS data. It's widely used sensor to estimate PM concentrations over the world. From January 2008 to December 2019 over the region from the NASA website. We use MODIS merge AOD products including both dark target and deep blue AOD based on the normalized difference vegetation index because we think that the region has different kind of land characteristics, so we think that dark target and deep blue combined product could be more useful over the region. We obtained both satellite data from Terra and Aqua satellite with a 10 km spatial resolution data for model development. Actually, this scan starts of MODIS sensor, including Terra and Aqua satellites, vary between over Turkey 7 to 12 UTC. We use some ground-based AOD data from RNS station, quality assured data for version 3 and level 2, validate our satellite data. Over Turkey, in the region there is no RNS station, however we two different RNS station over Turkey, we try to understand the data quality over Turkey and different region. You are seeing here the location of the RNS station. Southern part of Turkey includes a coastal rural site, and the inner part of Turkey has an urban side. And operation time of the RNS sites are really and ISO characteristic are really different from each other. We use a spatial temporal collocation method for AOD data. Because satellite-based data is a pixel-based data, however, ground-based AOD and PM concentrations are representing the point measurement, so we just try to spatially and temporally collocate information. We use the most commonly used method proposed by Ichoku in 2002. We create a 50 kilometer area around our and PM stations, and we calculate the valid and average AOD data located in a region, and we also use some temporal collocation information. We obtained meteorological data from MERA2 analysis, including PBS, solar radiation, pressure, wind information, precipitation, humidity, and like that. And also we included our model some aerosol characteristic, including total angstrom exponent parameter and surface mass concentrations of dust, sea salt, and sulfate. We also added the geographical data of land use parameter like elevation from GMTED and the NDVI from MODIS. So we calculate the NDVI computed for the 50 kilometer radius around each PM monitoring station like AOD data. We use also some spatial and temporal variables in our model. Special variables, latitude and longitude of grid cells. Temporal variables including cumulative dates, sea date, and representing the long-term trend and day of the year. We create a spatial temporal regression matrix was prepared by integrating geographical covariates including AOD, meteorology, aerosol fields, and some additional spatial and temporal information. We create two different data sets for modest terra and aqua satellites, because I said that before. We created intradaily PM10 concentrations because we try to understand the satellite over past time on the our estimation model. 10-kilometer grid was created over the region, and all variables calculated in the 50-kilometer search radius. When there was more than 100 sites in the same 10-kilometer modest grid cell, we calculate mean PM10 measurements. We calculate the average values and all observations used for modeling information. We use in the study run the forest model, subback decision tree model, and split the subset the features on each split. It's known that provide a highly accurate estimation results in the literature. When we look at our validation results, firstly, the data quality is different over the different kind of. In general, we can say that validation performance of AOD on coastal rural sites, dark and blue combined product perform better over the rural site. Actually, the urban sites show relatively lower performance, as you see here. However, the aqua retrievals show relatively high percentage of data samples within the expected error compared to terra satellite. It means that aqua provide more reliable AOD information over Turkey. We are seeing these differences in our random forest model variable importance scores, because the importance of AOD in random forest model indicated that variable importance can change by satellite over past time, and AOD is more reliable and more critical and the most important variable in aqua in the random forest model in aqua over past time. It's the consistent with the validation result actually. When we look at the test results of our random forest model, although statistically significant differences not found between terra and aqua model over past time models over the region, however, we can say that aqua AOD based random forest model could provide more slightly better model results over the region. And considering the national regional calibration of PM10 and AOD relationship, we can say that the best random forest model developed for entire region can explain the 53% of intradaily variability of PM10 concentrations with aqua AOD data. When we look at the time series of our estimated results for each satellite over past time, our model highly underestimated the higher concentrations and overestimated the lower concentrations over the region. Mainly the underestimation is more obvious, we can say. When we look at this site based on the forest results using the terra and aqua satellites AOD data, we can say that we can obtain a higher accuracy by individual site scale using the random forest model. For example, are up to 0.19 with terra AOD and 0.85 with aqua AOD, and actually the lower R values mainly observed around the highly urbanized monitoring site mainly located over Istanbul, I can say. When we look at the conclusion, This study provided a random forest model and to construct and decrease the uncertainty from some spatial temporal variations over the ground level PM concentrations. And this is the first study proposed to estimate long-term PM10 concentrations over 11 years based on AOD from different satellites in Turkey. Actually, PM10 AOD correlations are really low in Turkey, and aqua AOD representing the, maybe we can say the aqua AOD can explain the PM variability more than Terra products over the region. And our machine learning model results indicate that our model results show moderate capability to estimate PM10 concentrations over the region, and the model performance also shows some site-specific results. And also we show that performance of show the slight differences based on the satellite over past time. As we know, the relationship between AOD and PM10 concentrations mainly depend on the accuracy of the input parameters in our machine learning models. For example, mainly the satellite AOD data quality greatly impact our modeling results, and AOD data have some limitations and disadvantages, so maybe we should increase our AOD data quality over Turkey. For example, we can increase our iron stations over the region. Maybe we can try to understand the AOD characteristic under different conditions over Turkey. And the coarse resolution of AOD product maybe can cause some uncertainty in PM estimation and decrease our model accuracy. For example, recently, most of the studies use Mayak AOD data with 1 kilometer resolution, and actually they are obtaining a more accurate estimation results. Another limitation, I think this is the most important point, non-random missingness and some data gaps in AOD data, mainly affected by cloud cover, maybe the bright surfaces and high ISO loadings in using ISO algorithms. So this kind of limitations actually greatly affect our machine learning model performances. In the future, the predictive power of proposed model can be improved, maybe they generate more national and regional PM10 concentration maps instead of regional and site-based estimation results. Maybe improvements in the machine learning algorithms, like more advanced methods such as stacking more than one machine learning algorithm, stacking models can outperform our individual regional model. Maybe we can try the new things over the region or whole Turkey. Thank you for listening.
Okay. We have just 2 questions, which are just mine.
Yeah. Thank you for the question.
Sorry. So you underlined the improvement of the methodologies at the last part of your presentation. But can you explain the results on the variable importance scores? You said that from the analysis you got different scores regarding the variable importance. Can you give an interpretation of this kind of results? I cannot hear you.
Yeah. Can you hear me?
Yes.
No? Okay, thank you. We obtained the variable importance score from the random forest model. It measures actually.
What's your interpretation? What's your justification on your idea regarding your conclusion about the results?
I tried actually. I removed some redundant variable in my final model. Actually, I used some low scores and I removed this kind of variable from my model, and I obtained a similar R value in my final model. So just I remove, actually, I don't remember the number, maybe the 10 variable we remove the model.
Yes.
And it doesn't change our modeling results.
Yes. And what about the one of your final conclusion? You said that the method that you use decreases the uncertainty of the spatio-temporal variations, right? It was the first item of your conclusions. You said that the method, your method decreases the uncertainty of the spatio-temporal variations. Have you any evidence about this aspect?
Actually, I mean that I use some spatial and temporal variables into I integrated into my model.
Yes.
And I saw that these parameters increase my modeling results.
I mean, you because just you include more information about in the model, right?
Yeah, because AOD and meteorological parameters show some spatial and temporal variation over the region. Maybe temporal variation is more important because the region maybe.
I mean, you don't mean uncertainty about the estimation.
Yeah.
Uncertainty about estimation.
Yeah.
So you compare the uncertainty of the estimation of this method and the one obtained with other methods?
And no, actually, I mean that when I include this kind of variable into my model, it increases my model performances. I mean,
yes.
Yeah.
In terms of which kind of index you use
I analyze my random forest modeling results.
Okay. Yeah. Okay. Thank you.
Thank you.
Good work. Okay. So I think that we can go on. At the end, we have a poster presentation of Nadia Gammoudi titled Source Apportionment Simulation of Wind-Blown Sarin Dust over Central Europe using I-split model. You have just 5 minutes.
Okay. Just a second. Okay. Yes. Okay, thank you. Okay. No. Okay. So hello. First, okay. Yes. Thank you. Okay. First, let me start with a background information about the topic of this work. During many years, the North African dust, the North Africa represented a pump of a dust, a natural dust. This dust has This dust has crucial impacts on the climate change by absorbing, scattering the solar and terrestrial radiation, also by changing or modifying the cloud properties. To mitigate and characterize the essential role of this dust, it's important to identify and characterize the sources of this natural dust. Now I'm going to talk about the methodology of this work. So. In this work, we used the high-split model to identify the source of the the desert dust. The main steps of this work are the input of the necessary, the essential data for modeling, running the model. For instance, the meteorology data, the latitude and the latitude of the source, and go on, and so on. So the second step is the modeling of the run of the model for the model, and finally the display of the results. Moving on to the results, as you see here, this slide figures out the multiple forward trajectories simulation, respectively during 3 days and a long time simulation during a month. Both of the results show the variability of the distribution of dust simulation of dust, the wind-blown dust during the year. The main or the active season appears at the end of the spring or the beginning of the summer, and continue to all the autumn. Here, this slide can confirm the results showing on the previous slide, and we can conclude that when the dust storm outbreaks in Tunisia, firstly, the dust transported through the Mediterranean region, then across the Central Europe into the Central Europe atmosphere. Here, this slide actually collects all the animation simulation for the single particle concentration and the configuration of the mass concentration. The last here also the animation of the deposit, particle deposit of the dust just during the dust storm outbreaks. So now moving to the conclusion. To sum up, according to the results obtained, we can conclude that the dust storm's variation is related to both the meteorological condition and the variation of the season. Also, we can highlight the importance of the high-split model in the configuration and the following of the dust storming during a spatial and temporal simulation. So, thank you for your attention. If you have any question, you can contact me on the following mail.
Okay. Very nice presentation. Okay, let's see if we have questions in the chat. No questions. So thank you for participating to this section. Thanks a lot.
Thank you. Okay.
So again, thank you for participating and see you next year. Bye-bye.
Bye.
A short communication. Tomorrow in the morning, it should be an invited lecture given by José Antonio Centeno. I am in contact with him. He's having problem in recording his presentation. He will try to stand up for the night up to 4 o'clock because in USA there are 3 o'clock in the night, and so 45 minutes for the conference. So tomorrow, I don't know what will happen. I will let you know, obviously, as soon as possible. There are two solutions. The first one, we will have an online presentation. Please try to stay here at 9 o'clock. The presentation should be finished at 40 past 9. Then we quickly move outside of the hotel to take the bus that for the excursion to Alberobello and Polignano. Please bring your badge. That will be useful for the guide to identify you if someone will lost, as it is almost usual during the conferences. So see you later.